All right. Hello, everybody. Welcome to the next lecture of Chaos and Fractal Dynamic Systems. This is number 4. Last time we introduced a few things where we introduced the idea of one and two dimensional maps. We introduced the idea of chaotic state spaces. We introduced some ways of looking at dimension of fractals. We're going to clarify some of those things today, and just make sure that you have a good, clear picture of some of the things that are going on in all of these different systems. Because what will happen is that they'll build onto each other, and you'll begin to see some of that. If not this lecture, then the next one, how a lot of these systems are very closely related to each other, which actually ends up being kind of intriguing. So we are going to first go back and talk about the logistic map. Remember last time as we talked about it, we said that it was derived using a predator-prey model, which we call our prey. Let's just use circles for our prey. You have some population, like say deer in a national park, and if you leave these deer to their own devices without the introduction of predators, then their numbers will grow. And eventually, other resources that are there for them might start to become scarce, and disease would, also get passed around. And so you would have this growth, and as one, say, begets three, then you could see it would even be exponential growth. But then you introduce the notion of a predator species, and not as much, or as many, I should say, but some sort of predator. And then they began to reduce the number of prey, and their numbers can grow also, while the prey species are also growing. So this is predator. This is prey. And of course, when you have a situation like this, we say that they have been eaten. Now, that's bad for the prey, but it's good for the predator, and, keeping a balance is what it's all about. Now, I'm not trying to advocate for Thanos or anything like that, with those of you who watch the Avengers, but, you need a balance, and prey does it. Now, so, again, that the way that it has been quantified simply is this expression that you see here, this X being the number of prey species, given some factor that controls the expansion, minus the eating. So I guess births and eating. So it's exponential in that factor. Now, but it also was found that chaotic behavior happens. And I do want to again go back, and if you recall, we can figure out where the peak is by saying, and let's just use the value well, let's just use the regular value. So if you say y equals rho x 1 minus x, and you calculate dy dx, you'll get rho minus rho x. Now, if you set that equal to 0, then you can find out that at the point, you're going to always get x. Let's see, yeah. You're going to get rho equals rho x, and x equals 1. And why is that? Why doesn't that look right? What am I missing? I'm missing something here. Rho minus rho x. I know what's going on here. Okay, so you'll get when you take the differentiation, you'll get rho minus rho times x, which will be rho times 1 minus x. I'm still getting the same thing. We're trying to find the peak here, but the other thing that I gave you in the homework was finding, and this is what I want to focus on, is this fixed point here. This is the point where xn equals xn plus 1. This is the xn equals, or let's just say xn plus 1 equals xn line right there. So anywhere along this line, and where that line intersects the actual map, for whatever the values, you can see the map for different values of rho. And wherever it intersects is where this will repeat over and over again. And it's found just about that this point, rho equals 3.5694, such and so on, is where chaos occurs. So let's go here. This is a bifurcation diagram. I want to make a point, and then I'm going to jump out and show you something in Matlab. So we talked about last time having these this bifurcation and this period doubling. So here jumps to 2, and here jumps to 4, and even here you can see 1, 2, 3, 4, 5, 6, 7, 8. You see 8 right there, and so on. It doubles, but also, as I mentioned, out here you actually will get a period 3. So it shows that it doesn't just double into infinity. There's some points where a period 3, and period 3 can't come from a period doubling cascade. This is a period doubling cascade, it's called. And that's just basically saying it's going from 2 to 4 to 8 to 16 and so on and so forth. But obviously you can see that 3 will not come out of that, but yet 3 occurs, so there's something going on in here. So before we talk about another characteristic, let's take a look with Matlab. Now, my hope is that you have gotten access to Matlab that we've set up for you. Hope that is the case. If it is the case, we'll talk this through in our next discussion session. But MATLAB is just really a set of a programming language that allows you to do some pretty nifty mathematical operations, and it's completely unlimited. You know, whatever you can think of, you can almost do it. But the thing I like about it, you get to see stuff right away. Now, the way I'm going to do this with you all is not to say that you have to know how to program. You may, and that would be great if you did. But what we're going to do is, you know, I'm going to provide some basic code, just like what you see here. I'm going to make this available to you. And then you could modify these variables to see what it is that you want to see. Okay? So this one is you know, programming a logistic map. If you can see right here, R is equal to 3.89 is what I'm, you know, looking at right now. And we're going to iterate for 2,000 points. And this just pre-initializes the variable. This gives you an initial condition. Where are we going to start? As I told you before, if you start at 0, you're going to get nothing. So then this is to create the bifurcation diagram, which I'll show you in a minute. But let's just concentrate on the map. So this creates the map. You go from 1 to, in this case, 2,000. You calculate the value. Here's R times X times 1 minus X. And then I just give the value Y this value of xn plus 1 just so I can plot it easily. That's the only reason. Now I'm going to jump down to where we do the graphs. This will plot the logistic time sequence, and we can look at it in different ways. I'll show you the differences. And this plots the map. And then we'll get to the bifurcation diagram in a second. So in order to run it, you can either press run and it'll operate on the latest set of code you just put up here, or you could type the name in, which I called it logistics underscore map. Either way, and you'll run it. So I'm going to do that. It's taken a minute because it's actually doing a bifurcation diagram. I didn't stop it from doing it. And in a second, there you go. So let's take a look at, let's ignore this for now. Let's take a look at this. Now, as you can see, remember I used the value 3.8, well actually 89. I think I know why it's the wrong up here, but this is 3.89. You can see that it's almost at, you know, giving you a full parabola, but you can see these pieces are missing, right? There's gaps in here. There's places on this map that it's not visiting because it just never goes there. So let's play around with some of the values. I'm gonna make a quick change just so so this is done right. I'm gonna call this variable R. I'm gonna call this R. Just call it RS for stagnant or something. So here, I have to change it here. Change it here. This I don't want to change because this is for the bifurcation diagram. So I want to go down and for the map where I'm putting a number, this is going to be RS. So in this case, it'll separate that R value from the bifurcation diagram, which we're sweeping R, and I'll get to that in a second. But so, and the other thing I'm going to do, just so we can save time, I'm going to go ahead. No, I'm not. I'll just run it. Let's just run it, because by the time it takes me to tell you what I'm doing and actually do it, it'll be finished. So here, all right. So now you see this value is correct right here. Okay, so let's go back and let's change this a little bit. Let's change our S to something else. Let's make it 3.19. Okay, and I'm gonna run that, and we'll get to see what that looks like when it finishes. It's not finished yet. There we go. Now, as you can see here, you only get a few points. You only get a few points. Now let's talk about the bifurcation diagram, because we can look at them together and pick interesting spots to look at. The other thing I wanted to make sure I focus you on is what is it doing from time to time. We'll take a look at that also. And let me take what's now this bifurcation diagram. Now let me just describe what you're seeing here. So we're sweeping the value R, and then we iterate for, say 2,000 times for each value of R. And actually if you go back and look at the code, we're sweeping over the R value 10,000 times. Or we broke it up into 10,000 pieces. So there's 10,000 pieces between the start, which is 2.8, and the end, which is 3.8. So there's 10,000 sections. And for each section, we iterate it 2,000 times. So that's what we're seeing. And we can change this, and until you blow up the memory of your computer, you could try more and more stuff, and plus it'll take a little longer. But let's look at this. Let's look at somewhere at let's just say 3.5. Okay. What we should see is a period 4 emerge, right? So let's do that. 3.5. So we're going to run that. And let's see what happens when that comes out. Now, what happens is that first, let's look at this time stuff, or this is just each value of the sequence. You see it likes this point, it likes this point, it likes this point, it likes this point. Now, it's not exact, but they group around certain areas. So there's a grouping here, there's a grouping there. That's what it likes to do. And remember, there's 2,000 points here, but they're all kind of stuck in one area. If we go, this is something I'm going to do too. Let us zoom in on this bifurcation diagram. I'm going to start at 3.4 and go to 3.7. So let's say 3.4 to 3.7, but also let's zoom in our graph to make sure that that's what we're looking at. So we'll also say 3.4 to 3.7 in our axis, but also we got to make sure that we're zooming in there as well. So if I do 3.4 to 3.7, let's look at this area right here. Okay, so that is between, let's say 0.75 and 0.95. Let's do that. So let's say 0.75 to 0.95. All right, so we're going to run this, and we'll take a look at what the bifurcation diagram looks like, as well as the time sequence. Okay. So you can see it zoomed in a bit, and it only looked at, You see this period 2, 4, 8, and we need a few more data points, I guess. Let's try to do that. I'm gonna see how good I could push it in order to. So I'm gonna put a few more. Let's do 5,000. Probably means we have to. 50,000. We'll probably have to wait 5 times as long. But while that's running, we can talk a little more. All right. So what'll be interesting though is as you can see right here, this goes to 1, 2, 3. So even right here, there are points that kind of violate this period doubling root that we see that emerges right here. So somewhere within the chaos, you see a little bit of order emerge, and we'll see that a little bit more. But this gives you almost like an exploratory type tool that lets you play around and look at different aspects of this map and what it's doing. Now, if you go back and think about what we started saying, all right, looks like it's finished. So see, you can see you got a little bit more detail here, and it's clearly a period 3 that is emerged here. So this section right here might be pretty interesting to look at. And if you wanted to do that, we'll do it just for the sake. We're going to look at 3.62 to 3.65. And we're going to just iterate that part, 3.62 to 3.65. And we're also going to change our scale, how we're plotting it. 6.5, right? Let me see, does it need to, let's also from here, so this is probably 7, let's just say 7, 7.75. Let's say 7 to 0.9. So we're going to only look at 0.77 to 0.9. Now, again, we'll run it. It's going to take a minute. But what I was going to say is think about what it is we're talking about. If you remember, we're talking about prey and predators. So what would happen is if you the number of prey would kind of be fixed in this value given what we've established, then here the number of prey over time will change between this number and this number, and whatever that might be. And now here's 4 numbers that the number of prey could eventually settle to. And say for instance that settling time, that cycle time was every year, right? Or 2 years or 10 years, whatever it is. Okay, so now this just finished, and I want you to take a look at this. Inside of the area we zoomed in, look at what's happening. You see there is remember it jumped to that period 3, but then the single period takes on a period doubling inside. And I would imagine, and we could just keep doing this if we wanted to and just keep zooming in and recalculating. But inside of this, you see a whole different bifurcation route emerge again. And you probably can see the same thing that could happen up here, and up here. So, and down here as well, you can see that also. So it also has this self-similarity, this fractal type of self-similarity while we're doing this. Let's just play one, let's go a little further. I want to zoom in on this, but I want to recalculate so we can get a little bit more detail. So I'm going to go from 3.625 to 3.635. So let me pull this up and I can change it while we're looking at. I don't need all of this window size, so I can look at what I'm doing. So let's say 3.625 to 3.6, we'll say 635, and we will again do this same thing, so we can 635, but we're going to look at just this little window right here. So that falls within, well, within 8.2 and 8.6. We'll just do that. So let's say 8.2 and 8.6. Okay, so again, we'll run that, and while we're discussing it, it will emerge. But so there's this self-similarity, which again gives you this notion of a fractal bifurcation diagram, which tells you, again, remember, we're talking about actual prey or living beings or whatever, say they're deer, and the number of deer that will stabilize and emerge in that population. You know, that's what we're talking about here. So, you know, gets very, very interesting about how that. Now, again, it was a simple equation, but like this example. Okay, so here's zooming into that, and as you see, as we zoomed into that little piece, there then are more. And I would wager, and you can do this exploration on your own, and I'm going to challenge you to do that in one of your homework projects, is to zoom in and find these things, and then, you know, talk about what implications that means. So very, very interesting, but this was just an introduction. I'm going to provide the code to you and allow you to explore. Now here's another notion about this, and that is this exponential sensitivity to small changes when you're kind of in a state of chaos. Now this is for R equals 4, so the full bore map, and we looked at 3 points. So initially, these 3 points are very close to each other. You can see they're close to each other by a thousandth of a decimal point, right? 1.99, 0.2, 0.1. That's where we started, and the equivalent value for it. And then we then iterated this forward 10 times. And 10 times you see the difference between these points, and they're not a thousandth of a decimal point anymore. They are significantly distant from each other, and you can visually see what happened. So take this yellow point, after 10 iterations, here you are. You take this point and look at that, and so on. You could kind of do this, and you could see it with Matlab. Let's do this. Let's go back to this RS value. I want to make that 4, so we can kind of get the full map. I'm not going to do a whole lot of this because I just don't want the bifurcation diagram to slow things down. So I'll just change that back to like 5,000 because I'm interested in the map now. So I'm going to just run it, and then we're going to play with some of the numbers. So let's do that. Shouldn't take but a second. Okay, let me reduce that. So here's the map now for r equals 4. As you can see, it's almost fully spread out from 0 to 1 and from up to 0 to 1. Now what I want to do is look at some of the values. So as you can see, we have x, right? So we can just use that. So if I started off and said x of, let's just say 25. That value is 7.649. But if I say x of 39 or 35, you can see that's almost 0.0026, so it's way down here. So we started off at a point that was way over on this side, and it jumped over there very quickly. So this bounces around quite a bit. So there's this spreading that occurs, and this exponential type of spreading. That's what we're trying to demonstrate here. But if you find points that are fairly close to each other, and then you look at them, and we could have done that, I didn't want to take the time, but you'd have to find, say, 3 points that are close to each other, and then look at them iterated forward in the same number of iterations, how much different. Well, you could get a measure of what's called the Lyapunov exponent. We'll talk about that more later. And so you could very easily calculate how much spreading you actually get. And that's a measure. Now there's another map that I want you to explore on your own called the, well, two of them actually. One's a shift map, and I'll just draw it for you. Again, you're looking at x of n plus 1 versus x of n. And at the point 1/2, and here's 1. So I'll just kind of do a little dotted line just to make sure that you see what I'm doing. That's 1. So what happens is that this map does this, and it does this. And so between, so you have, x n plus 1 equals f of x of n, and that's equal to, and then this slope is 2, right? So it's 2x when 2 times x of n when x of n is less than 1/2. And what is it when, well, you can see it's just a shift, right? But it's 2 x of n minus 1/2. So, it just shifts it back, or shifts it over, I should say, when x is greater than 1/2. Now you can program that, and it'll do that. Now you'll see, and we'll find. I'll do a bifurcation diagram, and probably even update another Matlab code to do this map and show you what it does. And it actually has chaotic features as well. The other thing I wanted to show you just kind of visually what happens is that if you want to kind of see how these things iterate, you start, say with an input, we call this our initial point, let's call it x0, and you go up to the map itself. It says that this x value will give you this, right? And then what you do is you project that over to the x equals n line. I'm sorry, let's just say y equals x line, or you can call it x of n plus 1 equals x of n line. Right here, this fixed point, remember that fixed point? And then you go over there, and then you project, and then you project down and find the next point. Right there. So that'll tell you what the next one is. Then you project over to the line, project up, and do it again, and that's the next one. Then you go again. So you can see where this might spread apart, or it might decide to get drawn into this fixed point. But it's doing all this, after every iteration. So that's kind of what's, geometrically going on if you like to look at stuff like that. All right. So I hope you got a little more insight. I hope it gives you some tools, toys to play with MATLAB so you can see it. I wanted to go into the state space stuff, but I'll do that at the next lecture because it's going to be interesting. I want to go into the three-dimensional stuff and show you how you go from a three-dimensional flow to a two-dimensional map that ends up a lot like a logistic map, and you actually also see the bifurcation diagram, and you also can see the fractal and self-similarity type of nature that falls out of it, okay? And a lot of this you can explore with MATLAB as well as some other tools, but MATLAB is pretty cool to do that. I won't go into these now. One thing I do want to just clarify from last week's lecture, and I want to just make sure it's clear. So when we're calculating dimension is equal to the log of n over the log of what we'll just call epsilon. All right, what are these? So D is the dimension. N is the number of elements. And epsilon is this scaling factor, right? How big, how smaller, or how bigger or smaller, I guess, the pieces are. Now, you can do this. I want to go back to doing this square because I don't think I did it quite right the last time. And so first of all, so if you take n, you take epsilon, you take d, and we can call I the iteration number, right? So at the first iteration, you have 1, and this is 1. You have where there's no factor, so it's really moot at this point. But let's look at the second one, and what we're going to do on the second one is we divide it by 2 in each direction. So what do we end up with? We end up with 4 of these, but the difference in them is 1/2 in the length. Okay. because we only divided it by 2. So in this case, it's log n over log 2, or well, let me not n, because we know the number. It's 4. And we can see that's 2 dimensions. You do it again, but this time we're not cutting it up, the 4 into 4. We're cutting it, if we say 3, right, into thirds, that'll be the third iteration. But in this case, you've got 9, but the difference is 1/3. And in this case, log 9 over log 3, and that's still going to give you 2. So you can see it's 2 dimensions. All right, but now we go to a fractal, as we did before. Let's look at this one first, this Cantor set. You can start with a line. Now we're going to cut that line in half, but leave the middle third open. So this is, 1/3 in length of that. And then we could do it again. And that's now 1/9 of that length. But so this iteration is 1, 2, 3. The number of elements is 1, 2, 4. So in this case, log 4 over log 9, and actually I'll use Matlab to calculate it. And you get 0.63 as the dimension, which is less than 1. So it's less than a line, but it's less than a line, but greater than a dot, which would be 0-dimensional. All right, so it's not quite one-dimensional. A line is one-dimensional, and you can do the same thing for others. So I'm going to challenge you to calculate the dimension of the Sierpinski triangle, which we talked about before. And, if you remember that. What do you end up with as you go further and further? And this number gets cleaner and cleaner as you go higher and higher, because it's in the limit, really. So this really should be the limit as n gets higher, right? Okay, so I'm going to leave it here. Next time when we talk, we'll go back and discuss these 2-dimensional systems. I'm sorry, these 3-dimensional state spaces, or at least they live in a 3-dimensional area. They're actually fractional dimension, but they live in a 3-dimensional space. We'll talk about those. We'll have some relationships between that and the maps, and show you how they also are fractals. We can take up a lot of this at our question and answer, and please try to use Matlab. We created our IT department created a venue for you to use it, so please try to do that, and let's see how it goes. I want you to play with this, and again, as I said, I will post this code up on your in our portal, and you'll be able to pull it down and play with it as well. Okay, and we'll walk through that together. All right, that's it for today. Take care, and we will continue on.